I think there was a question, hey, is it a problem if I shut the valve on silane? Will I have a problem? It's only when it need to change? Okay. Oh, I'm sorry. I don't want to interrupt your conversation there. It's only when it's being released into air and it doesn't ignite. When you shut the flow, it will ignite. This is a cylinder in which we're going to release silane. For those of you that don't believe me, this is a silane cylinder. 1,000 psi. We're going to release it. And what's happening? Joule-Thomson expansion is actually liquefying the silane. This is liquid silane here. When I shut the flow, ignition. So that's the condition you want to avoid, is release, no ignition. When you shut it, it ignites. Okay? Pyrophoric gases can behave in a number of ways. Immediate ignition is what you want, but it may have delayed ignition. And what a problem with delayed ignition is what happens. You wind up accumulating a large mass, and that's when you can wind up with a dangerous condition. Auto ignition temperature of the gas will determine whether it's pyrophoric. Right? All flammable gases have a certain temperature in which you heat it, and at that temperature it's going to ignite when it mixes with air. Pyrophoric gases, by definition, are anything that ignites at a temperature less than 130 degrees F. Now, there are what we call self-igniters. Dichlorosilane, for example. What happens with dichlorosilane is when it releases into air, it reacts with the moisture in the air to become HCl. It's an exothermic reaction. The heat that reaction causes goes back into the molecule, and it then heats it up to the autoignition temperature, and the dichlorosilane will ignite. Okay, you can create conditions in which the material will ignite. Trichlorosilane, for example. People have taken trichlorosilane liquid, they've cleaned up a spill with spill pillows, and then they mound it in an insulated container. And what happens? The hydrolysis reaction continues on the spill pillow, and it self-heats to the autoignition temperature, and you wind up with an explosion. So you can create these conditions in some of your experiments and wind up into trouble. Flammable gas. We're all familiar with flammable gases: acetylene, carbon monoxide, ethylene, hydrogen. Again, the biggest hazard associated with these is flammability. Now, if you have a release, you can have an explosion hazard. Now, if you're using any of the silane compounds have very wide flammable range. But what's the other problem? The other problem with the silane compounds is that the oxidation reaction wavefront is much faster than propane. So the faster the flame speed, the greater the overpressure that can occur when you have the detonation.
Hey, Eugene.
Yes, sir.
Talk a little bit more about CO, because it's got other properties which also aggravate not just the flammability, but the toxic side of it.
Yeah, CO, we're all familiar with CO poisoning, right? Especially when you have a burner at home that is not properly ventilated or properly adjusted. And CO poisoning is essentially, what's it called? It's called a chemical asphyxiant, right? In other words, you don't have to have an overwhelming concentration of CO to be asphyxiated. What happens with CO? CO actually binds with your blood cells and prevents the uptake of oxygen. So if you get enough CO into your body, you die from asphyxiation because your blood can't carry enough oxygen into your heart, and you'll die from CO poisoning. Okay? It's a chemical asphyxiant.
So at UCSD, we do require, if you get a UCO, that it be housed and used in some kind of an exhausted enclosure leak check all the joints, because it's a tasteless, odorless gas that is toxic, and so you really have to manage it.
Yeah.
You have a lot of it.
Yeah, CO has no odor at all. I mean, I talked about arsine. Arsine has a slight odor. CO has none. So you don't even have any olfactory indication of CO as a toxin. And it could build up over time without you suspecting. So that's the hazard associated with CO. Flammable range, lower flammability limit, upper flammability limit. Now, you might get a cylinder in and it might say non-flammable gas. Is it flammable? That label is based on this definition. The problem is ammonia doesn't meet this definition. And as a result, in the United States, it has a non-flammable gas label on it. Just because it has a non-flammable gas label on it doesn't mean it can't be flammable under certain conditions. What you need to do is look at an MSDS sheet to make sure that it's not flammable at certain concentrations. The reason why I point that out is many of the replacement freons, they leave a hydrogen on it so it's not fully fluorinated. And as a result, it's flammable under certain conditions. So you need to be aware that many of these replacement freons exhibit the same property as ammonia. Hydrogen is probably one of the more severe hazards in flammable gases, much lighter than air, very wide flammable range. Now, low ignition energy doesn't take much to ignite a flammable gas. How much energy do you think it takes to ignite a flammable gas? 0.02 millijoules of energy. Now, you might sit there and say, well, how much is that? If I shuffled across the room and I shook your hand and I zapped you with static, how much is that? It's 200 millijoules. So I just zapped you with 1,000 times more energy than it takes for you to ignite a flammable gas mixture such as acetylene or hydrogen. Okay? That's why grounding is so important when you're dealing with these flammable materials. Okay? It doesn't take much to ignite these materials. Oxidizer. This is the opposite of flammable. It promotes the oxidation of a flammable gas. It accelerates the combustion. But more importantly, you should be aware that there are many gases that are considered oxidizers. Not only oxygen, it's chlorine. Chlorine is an oxidizer. Fluorine, chlorine trifluoride. Nitrous oxide, oxidizer. Nitric oxide, oxidizer. The key issue with these oxidizer gases is something which we call adiabatic compression. When you have a high pressure oxidizer and you design the system, if you don't design it properly, what can happen? You could wind up with a condition in which the high pressure oxidizer will compress very quickly, and in that compression, you'll heat the gas. Now, if the system is not designed properly, what can happen? You can heat it above the reaction temperature of the material, and you'll wind up with an oxygen explosion. This is a regulator that we're going to pressurize with oxygen, 2,000 psi, and that's an oxygen explosion. Now, what caused that oxygen explosion? That was contaminated with oil. Now, how do we make sure that a system is properly designed for oxygen? It has to be the right material. And aluminum is the worst metal you can use for high pressure oxygen. It can react with oxygen at pressures as low as 25 psig. Copper, brass, stainless steel are the preferred materials. You'll also have to clean the system. This is what we call oxygen cleaning. You'll see that there's an ASTM procedure on what to do to oxygen clean a system. So not only do you have to design it properly, you need to clean it. Now, there have been a number of regulator explosions because of poor design, or the people using the regulator didn't properly maintain it. They allowed it to become contaminated with another material, and there have been a number of regulators that have exploded because of that. So when you're using oxygen, something as simple as oxygen, you need to be aware that you have to properly clean. Even something as simple as nitrogen trifluoride, inert gas, but the adiabatic compression heat can get hot enough for it to decompose into fluorine. And you all know that fluorine is a very reactive gas. Oxygen will not react with stainless steel until it gets up to a pressure of about 725. Yet aluminum is as low as 25 psi. So material of construction is very important when you're putting together high pressure oxidizer systems. If you're using materials like chlorine trifluoride and fluorine, not only do you have to oxygen clean, you also have to fluorine passivate. Essentially, fluorine passivation is you're taking a low concentration of fluorine and you're reacting the metal surface to create a metal fluoride. This metal fluoride surface will protect the system from fluorine reaction when you flow the fluorine through. If you don't do this, what can happen? The fluorine will continue eating at the surface and you'll create a hole in your system and you'll release fluorine. So remember, oxygen clean. Now you also need to make sure that you select a proper metal. In most cases, it's Manel because the fluoride layer will stay intact. It's a very good surface area for fluorine. Nitrogen trifluoride have been a number of incidents as a result of improper cleaning or improper use of materials. Here we talk about adiabatic compression heat, and at high enough temperature, NF3 decomposes into NF2 plus a fluorine, and these are some examples of systems that have been destroyed because of an NF3 reaction. Incompatible. This was what happened here. What happened here is a lot of researchers say, I only want a little bit of gas, so I'm just going to open the valve just a little bit, right? It's a mistake. Your cylinder valve should never be used as a control valve. In this particular case, what happens is you have very high velocity gas that comes across the valve seat, which is KELF. You can create a condition which we call flow friction. High velocity gas will actually create a lot of heat. That flow friction started the decomposition of the NF3 and started the reaction on that valve seat. That then continued throughout that valve body and dumped the entire cylinder of NF3 into that gas cabinet. Okay, something as simple as just opening the valve just a hair. If you want to control your gas flow, use a flow meter or use a needle valve further downstream. Your cylinder valve is your primary safeguard. If something happens, you need to be able to close that valve, right? You should never be using the cylinder valve as your control device. Yeah, here. Flow friction destroyed an entire tube trailer. This happened in Japan. Just from something as simple as opening the valve, not enough. Here's one, another one. Yeah, these are just some incidents related to NF3. This is a code of practice for NF3. Anyone use nitrogen trifluoride here? Okay. Nitrogen trifluoride is a very common reactor cleaner that's used in semiconductor reactors. They use a plasma to break it apart into very reactive fluorine. Probably the more common material here is corrosive gas. They're either acid or alkaline gases. Typically, they're not corrosive when they're very pure, when they're anhydrous in the cylinder. But many are highly water soluble, and they'll become the corresponding acid or base alkaline solution when released into air. HBr, HCl, HF, sulfur dioxide are all corrosive acids. Gas corrosion. You probably all have seen things like this. HCl. These are HCl corrosion because of slow leaks over a long period of time. But the one that I'm most concerned with is HF. How many people use HF here? Okay. And what is your primary medical treatment for HF exposure? What do you do? Calcium glutamate, right? Now, what else? What's the medical protocol for exposure? If you suspect exposure, you flush, you start applying the calcium glutamate solution, right? That's your topical to start the neutralization reaction on the surface. What else should you not do? Don't give the person any painkillers, because the doctor's only way of knowing whether the treatment is working is if your pain goes away. Once you get to the hospital, they'll start to inject your glutamate solution into your skin in order to neutralize it below the skin. Now, how will you die from HF exposure? Is it because of corrosion? HF reacts with the calcium in your body. Calcium regulates your heartbeat. If the HF destroys all of your calcium, you'll die from heart failure. It's not the corrosive effect. It's because of the calcium that's being eliminated from your bloodstream. Okay? And the doctors can't replenish that calcium. That's the danger. So if you work with HF, you need to be aware of the medical treatment. HF cylinders explode periodically because what happens? HF, despite being a low-pressure liquefied gas, reacts with the metal, forms hydrogen over time, and what happens? In many cases, it's electrobottle. Researchers are finished with it. They can't return it to the manufacturer, so they stick it away in a drawer somewhere. And every couple of years, a university has an exploding HF cylinder. And that's because of the hydrogen pressurization. Now, here on campus, you have a policy, corrosive gas, maximum of 6 months. Okay? I would recommend that you take a look at the policies that you have in place, because you have a lot of good policies that will guide you to safe practices. Here is the statistic on explosions of HF cylinders at universities.
That was at Santa Barbara.
Yeah. I didn't want to indicate that, but
Yeah, it wasn't UCSD.
There was one in 2011 at a Big Ten campus that I took a look at as well. Many, many recalls. HF effect. They say if you have 25 square inches of exposure and you don't get treatment, you're going to die. That's essentially what you're saying. How big is that? That's about right, about like that. So let's say Doug gets splashed with hydrofluoric acid. What's the first thing you do? Do you grab him? You're going to get exposed, right? What do? You have someone that gets splashed. You got to get him to a safety shower. What else do you have to do? The worst thing you can do is pull that safety shower. The hydrolysis heat, when that water hits, will be severe. I had a guy, a chemist, that splashed himself with phosphorus oxychloride. The jar broke, saturated his lab coat. He hit that safety shower, and what happened? You've always been taught to pour water into acid or acid into water. What's the basic rule? Acid into water. What are you doing? You pull that safety shower, you got water into acid, and what happened was that hydrolysis reaction gave him second-degree burns across his entire chest. You have to get that clothing off, okay? You also have to protect yourself, because if he had hydrofluoric acid, you'll wind up with the same contamination, right? Here's a number of exposures, but this is the one I want to talk about. This person thought he got HF contamination from a vacuum pump that he was taking apart. When he got to the hospital, they shot 30 shots of calcium glutamate between his index finger and his thumb to neutralize it. In the old days, they would pull off the fingernail. In this case, they dug a hole to shoot it. I don't know about you, but if I had 30 shots of calcium glutamate, I don't know whether my pain would go away for a long period of time. But that's the only way a doctor will know whether the treatment is working. There's no medical test for HF exposure, okay? So if you work with HF, be aware of what to do if something should happen. Same thing. You guys use TMAH here, right? They use it in semiconductor for as a cleaner. TMAH is a liquid that is, the thermal hazard is so severe that companies like IBM have very special handling procedures. There were 3 fatalities in Taiwan. 3 workers in 2 cases got splashed with TMAH. Despite getting under safety shower immediately and going to the hospital, they died because of the dermal exposure. So if you work with materials, you should be aware of the medical treatment potential for exposure. Yes, sir?
What does that stand for? TMAH?
I'm sorry.
What does that stand for?
Trimethyl ammonium hydroxide. It's they use it in CMP. They use it as a cleaner for silicon materials. If you want, I'll give Doug an article that was written on that. IBM presented at CISA on TMAH hazard. Yes, sir.
I just want to follow up on something you said. If you do use corrosive gases, please do order in quantities that you can turn them over quickly. It wasn't that long ago where I had to figure out a way to disengage a corrosive gas from the system that had been left in place literally for years, and the valve became virtually unusable. So take a good look at it and make sure that you are ordering the
Yeah, you have an excellent program which we're going to continue to grow and expand, but it's only good if you know it exists, right, and you use it. Alkaline, ammonia, amines. But you also should be aware that ammonia will severely attack brass or anything containing zinc. So when you're handling these materials, you also need to know about incompatible materials. For example, what's the basic rule when you're handling acetylene? What is the worst thing you can use? Copper. You'll make copper acetylides, which are explosive. So the basic safety rule when you're handling acetylene is you don't use any copper compound, right? Ammonia, anything related to zinc. It becomes embrittled as a result of the ammonia. This is the dezinctification. Here you see fine cracking. So what happens? All of a sudden you grab that valve and it crumbles in your hand. Nothing worse than having a valve crumble in your hand, right? Gas cylinders, made to DOT specifications, carbon steel, many different specifications, both high pressure and low pressure, welded. Aluminum is very common, especially for high purity or low concentration mixtures. Fiber wrapped aluminum is typically SCBA cylinders. And then there are stainless steel and specialty alloy. There are many fluorine compounds that come in Manel cylinders because of purity. You want to maintain a very high purity, so they'll use a very expensive cylinder. Two types of cylinders, a returnable and disposable. What's a disposable cylinder? Disposable cylinder is an aerosol can, right? If you use an aerosol or a paint can, it's a cylinder because it's pressurized with a liquefied gas, right? Today they're using a flammable gas like butane or a mixture of butane and propane. In the past they used to use Freon until the ozone depleting rules came out. Here, you're using a lot of returnable cylinders. Typically, they're seamless or they're welded. Many, many different sizes. So, the typical high-pressure cylinder is a very rounded shoulder, concave bottom. Low pressure cylinder is a much broader cylinder and it's welded together and the bottom is probably concave, like you see here. And it has a foot ring on it in many cases. Many different specifications. And here at the university, you're not going to use the larger cylinders, but a lot of industry will use up to a 40-foot tube trailer. Or a rail car. A rail car will have 140,000 pounds of chlorine. So a lot of chemical companies will use rail cars of chlorine. 6-packs. And then cryogenic door. We talked earlier about cryogenic liquids that are in these doors. It's essentially a thermos bottle that keeps the cryogenic liquid cold, but a certain amount has to vaporize in order to keep it cold. So, you have a door, and this happens. Is this safe? What's going on here? For some doors, they actually have a pressure building coil in between the two vessels. And what that does is, if you're using a lot of gas, it'll take some liquid and vaporize it in the coil. And this is essentially the outline of the coil that's underneath the surface. Now, if you've lost the vacuum on that door, the entire surface would be frosted rather than just the outline. Cylinder valve, cylinder cap, you've all seen the markings. This is the specification, tear weight, and then the date of manufacture, and then after that you're going to see what we call the hydro test date. Typically, most cylinders are retested every 5 years. Campus has a policy that you don't keep a cylinder beyond the hydro test date.
I have a question.
Yes, sir.
A cylinder that's past the hydrostatic test date, that means it's no longer refillable, right? Unless you get it hydrostatically tested.
Could you repeat? I'm sorry. A cylinder that has...
That's past the hydrostatic test date
Mm-hmm.
is no longer refillable, correct?
Yeah, well, what the regulations say is that they can't refill it until it's retested, okay? So is it unsafe? It's not unsafe until it's refilled, but the campus has a policy that they don't want you to have it after the 5-year date, okay? So, but that's essentially what the regulations say. You can't refill it.
Is that a common regulation? I guess an industry.
It's a transportation regulation. Yes, sir. In fact, some countries are even stricter. Some countries have a 3-year retest requirement. So it depends on the specification of the cylinder. Okay. Yes, sir.
Yeah, the hydrostatic test date is interesting. It's hard for people to see, and frankly, if you don't know it's there, you'll never look for it. But
Well, there should be a ton of them stamped on the top of the cylinder.
it should be.
Yeah, I think one of the questions I was asked yesterday was how long can a cylinder be used for? I've seen cylinders that have a manufacturer date back to 1916.
They're all World War II era.
What's that?
A lot of them are World War II era cylinders.
World War One. World War One. The military used a lot of cylinders in World War One for both chemical warfare and for helium to fill the blimp, and so there was a lot of surplus cylinders that are out there. Yes, sir.
I know this was not 2009, but it was before 2009. I've seen it in 1909.
Okay.
And I've also had now 3 captured German tanks that had the swastikas on them.
Yeah.
That'll come through my lab as well.
Yeah. It's not as long as it's properly tested and maintained, the cylinder is still usable.
So is the policy is that we have to remove a cylinder if it's past the hydrostatic test date?
Yes.
You can start considering to send
Yeah.
it in, and I'll tell you why. It was about a year ago, I found a cylinder down in the bottom of Mayor Hall. It's been sitting there, with framing since 1975, never opened.
Well, that's not.
So you've got an economic issue as well as a safety issue. So what we encourage people to do is to pay close attention to the dates of your cylinders. Does it mean that we can't work with a lab if they've got high-value gas? We go possibly past that date? No. But we do encourage you to start pushing those out because we don't want to have an issue with them. And I've actually called the vendors and they say, yes, we need to go back.
Yeah, I mean, I think that's the concern. If you have a high value cylinder,
Yes.
it's not refillable, but it's still,
Yeah.
in working order, and you're still using it. How reasonable it is? What's that time frame? We have to get rid of that.
I've worked with labs that frankly have had some cylinders for years just because they use it as a standard gas and they can't afford to get rid of it. It's been their standard literally years, but it does present a dilemma. So, but we will work with you if there's one of those.
Yeah.
You also get charged for that hydrostatic testing. So
Yes,
if
you
you
do.
get, if you keep.
If you own the cylinder.
No, if you're renting it. If it's a rental cylinder that you've been paying rent on the whole time, you will get charged for the hydrostatic retesting if you've kept it past its date.
Yeah, just
Yeah.
think about it because there's real money associated with keeping, especially things like the cylinder I found in Mayor Hall was argon. And whoever bought that paid probably, I tried to calculate, it was over $3,000 or $4,000 over the lifetime of that cylinder for it to do what? Sit in this lab, unused.
Yeah, well, argon.
Yeah, we can talk more about this during lunch break. We can. Valve protection. The most common valve protection is the cylinder cap. Right, this is cylinder cap. It should always be on, except when you're using the cylinder, right? And now, why should you not pick up a cylinder by the cylinder cap? It's because many people think that the collar is an integral piece of the cylinder. It's not. The cylinder is made, and then the collar is put on afterwards. And look at the little ridge of metal that's actually holding that collar on. So if you're grabbing that cylinder cap, what can happen? You have 100 pounds or more that's pulling up against this little ridge of metal, and if there's any rust, what's going to happen? That collar is going to come right off, and you'll damage it. If you go to a gas supplier, you'll see we actually have cradles which we'll use to lift cylinders if we need to lift them in any position. So it's very unsafe to rely on the cylinder cap as a lifting device. I've seen facilities where they put an eye hook on top of the cylinder cap in order to lift it. Very unsafe. Cylinder caps are performance tested. So, you got a cylinder cap, it won't come off. How do you get it off? Stick a screwdriver in that vent hole and pull it off? Oh, that's what this guy did. What happened there? When he stuck the screwdriver in, he wound up opening the handle of the silane cylinder, and now what do you got? You got a stuck cylinder cap, and you got flames coming out of the cylinder. Now, how do you shut that thing off? You can't get the cap off, right? Fire department came, they said, we ain't touching that. This thing burned for over 8 hours. Meanwhile, the fire department stood by to make sure it didn't explode. Emergency response team said, I ain't touching that either. So, if you have a stuck cylinder cap, you have to use the proper tool, a spanner wrench like this, which will hook onto the cylinder cap, or a strap wrench, right? You should never stick anything inside that vent hole, because you can create that condition. There. You think that's suitable? Huh? Well, at least he was trying to follow policy, right? Cylinder valves, there are many different types of valves. I'm not going to talk about these here. You should just be aware that there are metal diaphragm packed and pressure seal, as well as valves in which you can take liquid out or gas out on the same valve. Typically, refrigeration repair guys will have a cylinder with that type of valve. Now, campus has a policy that discourages the use of lecture bottles. And what is a lecture bottle? A lecture bottle is essentially a small cylinder with a valve that is wrench operated. This is a lecture bottle valve. It's not a very robust system, prone to leaks and prone to incompatible gases being put into it. So this is a wrench operated valve on a lecture bottle. Pressure relief device, used to prevent cylinders from catastrophically failing in a fire. In the United States, it's required for most cylinders, but you can't put it on zone A poisons. Arsine, phosphine cannot have a pressure relief device. Use varies around the world. Europe doesn't allow pressure relief devices for anything, whereas in Asia, they require pressure relief devices for everything. So if you do any international work, you'll see significant differences between countries. Rupture disc is the simplest. It's a frangible disc that ruptures, or fusible plug that melts at 165 degrees or 212. Typically, chlorine, ammonia as a fused metal device. Or a combination that's got fused metal and a rupture disc. Hydrogen, silane, boron trifluoride have a combination device. It requires high temperature and high pressure. So, what do you see here? What's happening here is the metal diaphragm got damaged somehow. And fused metal will actually extrude under high pressure. Now what's happening here is this is the fused metal being pushed out of the pressure relief device. It's an indication that this pressure relief device is going to activate at any point. This emergency response team did the right thing. They didn't move the cylinder. They dumped it while it was in the gas cabinet. Now, why is this important to you? It's important to you because this is one of the safety inspection things you should do when you do your walk around. Why is it important for UC? When I did the training class up at UCI, they asked me to walk around and take a look. And I found a hydrogen cylinder with a extruded pressure relief device that was ready to activate, sitting in a laboratory. Okay, I have a picture of it. I'll show you what, I don't think I put that particular picture in. Whoop. This is a normal pressure relief. The fused metal should be flush with the housing. This is one that is extruded. You see the plug starting to move out? It's being pushed out of the... That's an indication that that metal rupture disc has somehow failed. And at some point, you're going to get leaking gas. Okay? So this is... We'll put some examples in your website so that you know what to look for. But that's a problem that I've seen in a couple of locations. Spring-loaded device. This is a propane cylinder valve. We won't talk about size up. This is actually a propane cylinder venting through a pressure relief device. Happened to be a McDonald's, but the guy was going through the drive-through. And you see it vents and then dies down. The spring-loaded device will shut off and then reignite. Now, if that goes on long enough, what's going to happen? That cylinder is going to explode because you vent enough propane out of there, the metal fails, you're going to wind up with a blebby. And that's exactly what happened here. We don't have time to watch this particular video, but you should just be aware of that as a problem. Outlet connection. Different outlet connections are used to prevent incompatible gases from being connected together. Now, the fundamental safety rule worldwide is a flammable gas has a left-handed thread. How do you tell it's a left-handed thread? There's a notch on it. And in fact, I saw a few gas cabinets in which they put a reminder to folks that it's a left-handed thread. Acetylene has a left-handed thread. Hydrogen has a left-handed thread, right? Now, for those of you that have propane grills, the old OPD valve, they were going to ban propane grills a number of years ago because consumers were not used to a left-handed thread. And they wound up with a lot of leaks and explosions. This is the only right-handed thread for a flammable gas, and it's only for consumer propane. Hand tight. Only 20-pound propane cylinders for your propane grill will have this. If you have a forklift with propane, it still has the old CGA 510 connection. CGA 510 connection valve that is used. Oh, this guy right here. This is the old CGA 510. So you'll see that on acetylene and you'll see that on propane. Now, a couple of different types of connections, bullet and gasket. But what's the thing that I see that many users make a mistake on? This is a CGA 580 connection. It's used for nitrogen. And what do you see here? Teflon tape. Many people mistakenly believe that the seal is from the thread. It's not. The threads provide mechanical strength to deform the nipple against the valve. That's what where the seal is. Now, if you put Teflon tape on, you could prevent this from being tightened enough, okay? So yesterday I took a picture of someplace that had Teflon tape. It's a very common mistake that people make, okay? I walked around another lab, a national lab, and I found this, but what else? This researcher made a bunch of adapters to adapt to the regulator. What else did I see? This is a station regulator. A station regulator can only take a pressure of 200 psi. Cylinder's 2,000. Okay? If the researcher, he was trying to save money, and I said, well, when you open that valve, that thing's going to explode. So, needless to say, he took that back apart, but here's one. Nice connection, huh?
So when can you use, when is Teflon appropriate?
I'm sorry.
When is Teflon tape appropriate? What kind of tanks?
Teflon tape is appropriate when you have what we call an NPT connection. NPT is a national pipe thread. It's a tapered thread that are used for threaded pipe. And the seal is when you deform the thread. It's at a taper. And as you screw it in further, it forces more and more thread to be deformed. So it's national pipe thread, NPT thread. But that's typically, like for your gas piping system, is what you would use Teflon tape for, not for a CGA connection. Okay? I'm sorry.
Not to the tank, it's
Right.
past the tank.
Right, past the tank. Here's one. I walked around and did a safety inspection. What do you see here? When I walk around, I look at everything, and the gauge is blown. The researcher overpressurized the gauge, and it spun. That's what we call a spun gauge. Now it no longer works. So what's it telling them? It's not telling them anything. This needs to be replaced, right? Never rely on cylinder color for identification. The label on the cylinder or stenciling is what you should use, okay? And you're seeing these hazard labels. But more importantly, most gas cylinders will have shoulder labels, because when you nest a bunch of cylinders together, you can't see the side labels. It's easier to see the shoulder label. And GHS we talked about earlier. This is the globally harmonized system. And what's it do? It's coming up with new pictograms. You'll start to see these. These are the additional hazard warnings for carcinogenity, mutagenic effects, etc. Safety data sheet will change as a result. Just remember, there is not a color code in the United States. Cylinder handling, is this safe? Is this legal? Under the regulations, this is illegal. This is 150 kilograms of silane.
The horse is in there.
Since it's less than 1,000 pounds of a flammable gas, it doesn't have to be placarded. They don't even have PPE on, right? If you're moving a cylinder cart is absolutely critical. You think that's safe? So, you have a lot of guidelines on storage, transportation, etc., I would recommend that you take a look at your website to become familiar with all of those. And as I said before, you have some very good policies and guidelines in place. Just become familiar with them, right? What I'm going to do tomorrow is expand on those so that we add additional materials or classifications. Okay. So, with that in mind, I think we're at about 12 o'clock. I don't want to keep you from lunch. I'll entertain any questions from anyone that has them while I'm packing up. And for those of you that I'll see in the afternoon session, I'll welcome you there. So,
Everybody signed up, though, everybody got their name on there. 1:30 back at Pack Hall for those people that are coming up, so we'll do that at the hall.
okay. Thanks again. Thank you.